Hi everyone, I am Marivuli, a master student at UC San Diego, and in this video, I'm going to share what I learned about random processes and its application in real life. Note that this content is only for educational purpose, and it's not a recommendation or endorsement of betting and gambling. Always perform your due diligence and consult with professionals if needed. So let's get on to the problem statement. Imagine you're at the roulette table with 1000 units of money. Your goal is to walk away with more money than you started, no matter how long it takes. In roulette, players bet on where they think the ball will land on the spinning wheel. The dealer spins the wheel in one direction and rolls the ball in the opposite direction. The ball will slow down and land in one of the numbered pockets. The number and the color of the pocket where the ball lands determines the outcome of the spin and which bets win. You can place various types of bets, each with a different chance of winning and each with different payouts. Now our question is, what's the optimal way to use the 1000 units? So before going into the question, let's briefly look into the types of bets that we can place. Let's take a look at the different types of bet you can place in roulette. Starting with a straight up bet, that's just a bet on a single number. It has the highest payout of 35 but also has the lowest chances of winning, just 1 in 37. Then we have the straight bet which covers 3 numbers in a horizontal row. Then we have the corner bet where we bet on 4 corners of a square. Next, we have the 6 line bet which covers 2 adjacent rows, covering 6 numbers in total. Then we can place bet along a column of 12 numbers. And finally, we have the even money bets, red or black, even or odd, low or high. These bets cover 18 numbers each and pay 1:1. Note that even after betting on 18 numbers, you still end up with less than 50% of chance. Now that we have complete understanding of the problem, we can explore how to develop a strategy using mathematical tools. Let's take a look at how wealth changes after placing a bet. Suppose the wealth at time t is denoted by xt and you place a bet ut at time t having a payout ratio of p. It is the indicator variable which denotes the outcome of the event. If we win, it's 1 and if we lose, it's 0. So we have the wealth xt, then we place a bet ut, so we are subtracting it. And if we win, we get a payout times the bet amount. And if we lose, we don't get anything and we lost the bet amount. So we multiply it by it. So we got this equation, wealth update equation, and we express the wealth update equation in terms of change in wealth to make our analysis easier. Where if we win, the change in wealth is this much, and if we lose, we lost the bet amount. We have this wealth update equation which says if you win, your wealth will increase, and if you lose, your wealth will decrease. So this creates a sequence of wealth indexed by time. So the question is, can we analyze this sequence using the ideas from the deterministic sequences? So let's see. Sequence is an ordered list of values usually generated by a fixed rule. Yes, ours follow this rule, like arithmetic sequences and geometric sequences. And second, it must be entirely predictable. Is it predictable in our case? Unfortunately, no, because we don't know the outcome before the event happens. You might assume a fixed pattern of outcomes, like when, then we are losing, then we are winning, then we're losing, and so on, 1 and 0. But this assumes we know the outcome of the event ahead of the time, which is unrealistic. So we need better tools to analyze this problem. We must treat the wealth evolution as a random process where the wealth at each step is a random variable. The value of the random variable is uncertain and it's governed by a probability distribution. And in this case, the value of the wealth is governed by the probability of the outcome. Random processes can be seen in things like temperature, signal noise, and stock prices, and so on. Now that we are clear on how wealth evolves, let's look at the equation. We assume the wealth at time t is fixed, so we can't change it. So the variable it is stochastic in nature, so we can't control it. So what we have in our control is the bet that we place at time t. The bet must be less than the total wealth at time t. So what all types of bet you can place? One of the trivial bet is the all-in. So we will be looking into this bet in our analysis. Then we have the fixed bet where we place a constant bet irrespective of what happens. Then we have the time dependent bet where we change our bet as time passes. And finally, we have the wealth based betting where we bet based on how much we have at that time. In this video, we will be exploring a betting strategy of the fourth kind, specifically the Kelly's betting strategy. The Kelly's strategy uses a proportional betting where the fraction of wealth that we bet is between 0 and 1. The Kelly's strategy aims to maximize the long-term capital growth. Let's derive the Kelly's formula for a single bet. We have the wealth xt at time t and let f be the fraction of wealth that you are going to bet with the odds ratio of p. The indicator variable takes the value of 1 and 0 with the probability p and 1 minus p respectively. If we plot the distribution, we will get something similar like this. We have I, then probability, 0, 1, 2 values. And this type of distribution is known as the Bernoulli's distribution. We also assume that the sequence is independently and identically distributed. It means that the sequence I0, I1, and so on values are independent and are sampled from the same distribution. And in our case, it is the Bernoulli's distribution. The, the IID assumption is realistic in this context, as each spin is independent of the other and governed by the same probability distribution. Let's take ut equal to f of xt, and then we have the wealth update equation as shown below. And let's take xt common, and we would have xt plus 1 equal to xt times 1 plus f times p minus 1 it minus f minus 1 minus it. Assuming xt is not equal to 0, we would get the ratio of xt plus 1 and xt. We can see that the ratio is greater than 1 if we win and less than 1 if we lose. We know the initial wealth x naught, then wealth at any time x t equal to n is given by x naught times x1 by x naught times x2 by x1 times x3 by x2 and so on till xn by xn minus 1, where we can get the ratios from the above equation we have just derived. Now that we have the wealth at time t equal to n, what can we say about xn? We can't comment anything about xn using this relationship. Why? Because the value of it is random and we don't know how to handle it till now. So to understand the behavior of xn, let's look into the strong law of large number. The theorem is simple. If you have a sequence of IID random variables with expected value of mu and that value is finite, then the sample average up to time n will almost surely converge to the true value as n tends to infinity. We will be using this theorem in our analysis. So we have xn by x naught equal to product of t equal to 0 to n minus 1 1 plus f times p minus 1 it minus f times 1 minus it. So how can you use our law in this case? So for that, let's take log on both sides. Log of xn by x naught equal to then the product becomes the summation running from 0 to n minus 1 log of the value. So we have this for summation. So we got the log ratio as a sum of sequences of random variable. Let's denote this random variable as yt. And if we denote the sample average as Sn equal to 1 by n summation of yt t equal to 0 to n minus 1, then this is the summation of t equal to 0 to n minus 1 yt, which is just n Sn. So we represented the log ratio with the sample average. So if you use a sample average to calculate the wealth at time t equal to n, we get xn equal to x naught times e power n Sn, where Sn is the sample average. Using the strong law, we can infer that the sample average will almost surely converges to the true average as n tends to infinity. Why? Because the why it's true, why this is true? Because the random variable yt is IID, and why the random variable yt is IID? It's because the underlying random variable, the indicator variable, is IID. So we can find the expectation of yt using the definition. Expectation of any variable x equal to summation of p of phi x of phi I, where x of phi is the value of x with the probability of pi, and we are summing over all the values. In our case, we have two values for yt, as there are two values for it which are 0 and 1 with the probability of 1 minus p and p respectively. We get the expectation of yt, which is the true average mu. So we have xn equal to x naught times e power n Sn. And strong law says that Sn will be true average for larger n. For then x n tends to x naught times e power n mu for n large n. So if mu is positive, then x is time. Then the wealth will explode. And if mu is negative, the wealth will go down to 0. So from this equation, we can see that mu determines how fast or how slow our wealth changes, and it is a function of the fraction f. So this is called the expected growth rate. So we have the expected growth rate g of f equal to p times log 1 plus f times p minus 1 plus 1 minus p times log 1 minus f. To grow our wealth over time, we want to maximize this growth rate. Taking the first derivative, dou g by dou f, and equating it to 0, we get, if we solve for f star, we get the extremum point, and we can verify that this extremum point is a maxima using the second derivative test. So we got the Kelly's criteria for a single bed. If the fraction is between 0 and 1, and if we obey the fraction, then according to the strong law, we can ensure that we can get infinite wealth if we wait for a very long time. The graph shows the behavior of growth rate as a function of f. We can see the growth rate increases till the maxima and then monotonically decreases after the maxima. The growth rate is positive till the critical fraction, and any bit made with the fraction less than the critical fraction, less than fc, will result in a positive growth rate. Note that at f equal to 1, the all-in strategy creates infinitely negative growth rate and will always result in a ruin in a long time. We will apply the Kelly strategy in the case of 6-line bet. We have the Kelly's fraction here, and we said that if f star is greater than 0, then we have a edge and we should bet. And if we get f star is less than or equal to 0, then you should not bet. Our assumption we made in the derivation do not hold here. So the 6-line bet covers 6 numbers out of the 37, and the chances of winning are 6 by 37. So we have a payout of 6 for this bet. The Kelly's fraction is shown here. If we simplify it, we get a very small but negative number. So since the Kelly's fraction is negative, you should not take this bet for the purpose of long-term capital growth. You can try with other bets. Note that if the payoff is slightly more than 6, then this bet seems favorable even with the 16% chance of winning. So, and we'll be seeing this in our simulation. So the single bets are not favorable for us, then what about if we bet on multiple groups of numbers? So let's look into specific case of betting on mutually exclusive events. Mutually exclusive events ensure that only one outcome can occur and there is no overlap between any two outcomes. So we'll be following the procedure that we followed for single bet. The first step is to find the expected growth rate function, and then we have to maximize it. We can construct a wealth update equation for m mutually exclusive events where we place bet ui equal to fraction fi times the total wealth xt. Now that we have the wealth update equation as shown here, taking the xt common and finding xt plus 1 by xt, and then we can find xn by x naught. To use the strong law, we take the log and use the logic flow that we have seen in the case of single bet. And if you use the log, we get the new random variable yt as the log term and the sample average derived for the derived for the sequence yt. Then we need to find the expectation of yt, and the definition says that we have to sum up the probability times the value for all possible scenarios. So in our case, we have broadly two scenarios. First, there exactly one event we bet on occurs and all others do not happen. There are m such possibilities as there are m mutually exclusive events. And second, there is also a possibility that none of the events that we bet on don't happen. So for the first case, let's find the probability using the Venn diagram. For example, the probability that event A happens and event B and C don't happen can be visualized in this Venn diagram. Probability that event A happens and probability that event B don't happens is in this fashion. And probability that event C don't happen is in this fashion. So from the diagram, we can see it is just the probability of event A happening. And because why this is the case? Because it is due to a mutually exclusion assumption. So generalizing it, we can get the probability of event I happening and event J not equal to happen. I don't happen. It is just probability of event I happening, and in our we denote it using Pi. For the second case, we are interested in finding the probability of all events not happening. So, for example, probability of event A not happening and event B not happening and event C not happening. It is just this area, which is 1 minus probability of event A or B or C happens. And due to the mutually exclusion assumption, we'll get summation of probabilities. So using the probability that we have found and the yt in those cases, we can get the following expectation. So this is from the case 1 where the probability of each event happening is Pi and we are summing over m mutually exclusive events. And the probability of losing all the bets is this one, and the value corresponding to the event is log of 1 minus sum of all fractions. So we got the expected growth rate g of f. Then our next step is to find the maxima such that it follows maxima f such that summation of fi is less than 1 and all fi's are greater than 0. So we can do this analytically and or numerically. One observation we have to note that is that the g of f is concave and the constraints form a convex set. So the maximization problem is a convex optimization problem. And it has a global maxima. If we go by the analytical method, we have to find the extremum points from the first order derivative and we have to check the Hessian for Hessian whether it is maxima. I have derived the optimal betting fractions for the case of 3 bets analytically using the SymPy package. The full derivation is available in the GitHub link below. From this, we arrive at the following results. Let's look into the simulation of Kelly's strategy and compare the case if we don't use Kelly's. Let's use the case of 6 line with the payoffs modified. We simulate it for 40 time steps and 1000 samples. And Kelly's function comes out as 0.009, a small value but a positive value. And let's compare the case if we wager half of our wealth at all time. So from our calculations, we can see the Kelly growth rate is small but positive. But in the case of betting half of our wealth, we end up with negative growth. We will verify the results of our calculation using the simulations. The simulation shows that the number of samples where it went zero is smaller than the case where we bet 50% of our wealth. In just 40 time steps, betting half of our wealth each time will often lead to ruin, even though there are some sample pots where we reach extreme wealth before collapsing. In contrast, using the Kelly split results in a more stable and gradual increase in wealth over time. Note that the time step t equal to 40 is relatively very short time horizon. If you are interested in exploring the behavior over long time periods, you can access the Python scripts used for the simulations in the GitHub. Now, if we consider the case of multiple bets, we can apply this to real roulette strategy. A 6-line bet covers 6 numbers, and by placing 3 non-overlapping line bets, we effectively cover 18 numbers, which is nearly half the way. So let's check the Kelly's fraction for the same. The parameters for the three different 6-line bets are the same. Each has a 16% chance of winning, giving 6 to 1 payoff. If we substitute the parameters in the formula we have just derived, we get the fractions to be nearly 0 and this negative. So even after spreading our bets, the expected growth rate still comes out to be nearly 0 or negative. This means the odds and payoffs in roulette are fundamentally against us, and over time, if we are not careful, the house edge can lead to inevitable losses. The Kelly strategy is powerful, but it has its own pros and cons. The pros is that it can maximize the long-term capital growth and it can avoid bankruptcy in the long run. And finally, it cultivates discipline in risk taking. The cons is that we need to accurate estimate of probability. Consider the example of a single bet where our estimated probability suggested a positive growth rate. However, if our estimate differs from the actual real world probability, we may unknowingly be operating in a region with negative growth rate, leading to losses. The second con is that the Kelly strategy can be volatile in the short run, which can be alleviated by following the fractional Kelly, where we make bets fraction of what our Kelly strategies suggest. So this ensures that the volatility are less, but at the cost of lower growth rate. This video uses a casino game to explain Kelly's betting, but the main idea also applies to investing. A systematic investment plan or SIP follows the same logic as Kelly's strategy. You invest a fixed portion of your income at regular intervals, regardless of market ups or downs. In this video, we also saw an example of diversification by spreading bets across different outcomes. The same idea applies to investing, where we spread money across different assets like stocks, gold, and bonds, helps reduce overall risk. And finally, successful investing is about finding opportunities with a positive expected growth rate over time. Remember, smart investing, like smart betting, isn't about luck, it's about making disciplined decisions based on probability. Thanks for watching. If you enjoyed this video, feel free to share it and spread the knowledge.